Hey guys, the purpose of this video here is not any additional instruction. I wanted to give you guys an answer key to the end of the year assessment study guide, but give it to you in a format that's a little bit easier to follow than just copying down the answer key that I have written out. So I'm going to go through each one of the problems in the end of the year assessment study guide one by one. Remember, the end of the year assessment is going to cover just second semester content, everything that is in the second semester. So this is units 5 through 9. This study guide is a comprehensive list of things that you could see on your end of the year assessment on June 8th. I did give out a single assessment study guide for both honors and school level courses. As we go through, I will differentiate the questions for my school level guys that are good review but are not going to be part of your requirement for the end of the year assessment. So let's go ahead and let's get right into the first problem. The first problem tells us to complete each of the following using long division and then to check our answer using synthetic division if applicable. So long division and synthetic division are both important. We need to use both. Synthetic division is definitely faster, but sometimes we can't use synthetic division, which we will see in this problem, and then we have to use long division. Remember some terms. The number that we are dividing by, or the polynomial in this case, x minus 2, this is called the divisor. The number that we are dividing is called the dividend. So when we complete long division, we want to put the dividend, the entire dividend, underneath the division symbol. In this, notice our polynomial that's being divided, x cubed minus 4x plus 5, skips the term x squared. Essentially, there's 0x squared as one of these terms. So generally, we don't write that down, but I'm going to put it down here as we do long division in case we need the placeholder. So the dividend goes on the inside of the division symbol, the divisor on the outside. Now, to come up with a quotient, which is the answer that we're looking for, the number that's going to go on top, what we need to do is compare the first term of the divisor to the first term of the dividend. Basically, we need to see what is x cubed divided by x, or what times x would give me x cubed. If you said x squared, that would be correct. So x squared is the first term in our quotient. Now, what we do with this x squared is we multiply it to the divisor. So I'm going to take x squared times x and x squared times negative 2. So x squared times x is x cubed. X squared times negative 2 is negative 2x squared. We are then going to subtract both of these terms. So that changes the positive x cubed into a negative and the negative 2x squared into a positive. As I subtract these terms, I'm going to be left with 2x squared minus 4x plus 5, bringing down the other two terms of the polynomial. And now I want to repeat the process. So now I'm comparing the first term of the divisor, x, to the first term of the polynomial that remains, 2x squared. So if you said 2x squared divided by x would be 2x, you'd be correct. So now again, I take this 2x and I multiply it to each term of the divisor. So 2x times x is 2x squared. 2x times negative 2 is negative 4x. I subtract these terms. Subtract both, so I need to make sure I change the sign of both. So what would happen here is now the 2x squared minus 4x would cancel out with the negative 2x squared plus 4x to give you 0. I'd bring down one term remaining, and it would just be a positive 5. So this positive 5, we compare that to the divisor. There is not a value other than a fraction that would multiply to x to give us a positive 5. So this is our quotient, but it's got something left over called a remainder. So generally how we've been writing it is the quotient, x squared plus 2x, plus the remainder, 5, over the divisor, x minus 2. So our final answer here would be x squared plus 2x plus 5 over x minus 2. And this is how we can complete the problem using long division. We can also complete this problem using synthetic division. Remember, with synthetic division, instead of working with the entire polynomial, we work with only the coefficients of the dividend. So if I go back to this polynomial, the coefficients of the dividend are 1, 0, because remember there's a 0x squared, -4, and then 5. So I take 1, 0, -4, and 5. How I write this in synthetic division is I take that division symbol and flip it upside down. I put a box generally under the last term because that's going to remind me that's my location for my remainder if there is one. Now the number on the outside, it's going to be just a number for the divisor, is not the coefficient of the divisor. This is where sometimes people mess up. Remember, to get the number on the outside, we actually take the solution, the 0 of the divisor. So if I did x minus 2 equals 0, I would add 2 to both sides, so x equals 2 would be my solution, or my 0 for the divisor. So on the outside of this division symbol, synthetic division symbol, I'm going to put a 2. Now for synthetic division, we add down the columns and then multiply by this number outside that is the divisor. So if I look in the first column and I add down the column, I have 1 plus, there's nothing there. So basically this first term comes down. Now I take this 1 here and I multiply by the term for my divisor, 2. So 1 times 2 is 2. That goes in the next column. And then I add down that column. 0 plus 2 is 2. And now I multiply. I take this 2 and multiply it to that one. 2 times 2 is 4. Then I add down the column, gives me a 0. And then I repeat one more time. I take that 0 times 2, which is 0. I put it in the next column. Then I add down the column. So what this gives me is coefficients for my quotient. So my quotient would have 0 for a constant term, 2x, and 1x squared. So x squared plus 2x. It does have a remainder, and this remainder 5 we would still write over the divisor. And so we get the same answer either way we work this. So this is an example of both long and synthetic division. Now, in B, we're going to do this problem with long division, but we're not going to do this problem in synthetic division because synthetic division does not work for problem B. Synthetic division we're only able to use synthetic division when you divide by a term that is of degree 1 or has 1 0. So x minus 2 is of degree 1 because this is x to the first power, so I could do synthetic division, and we did. In B, the divisor is x squared minus x. This is of degree 2 and has more than 1 0, and so there is no way to do synthetic division that we know of with this problem. So instead, what we will do is long division. So the only way to solve this, based on what we know, is long division. So let's take x cubed. I'm going to put in 0x squared plus 2x minus 4 for the dividend. And put that underneath the division symbol. And my divisor is x squared minus x. Now I can compare the first term of the divisor to the first term of the dividend. So x times x squared would give me x cubed, or x cubed divided by x squared is x. So my first term in my quotient is x. So I take this x and multiply it to both terms of the dividend. Or sorry, to the divisor. X times x squared is x cubed. X times negative x is negative x squared. I need to subtract both of these terms. And that would give me, the x cubes would subtract to 0. That would give me x squared plus 2x minus 4. I repeat the process. So compare the first term of the divisor to the first term of what is remaining with my quotient, x squared and x squared. So multiply by 1. X squared times 1 would give me x squared. So then take that quotient 1 and multiply by x squared and negative x. So this would give me an x squared minus x. I'm going to subtract both of those, so it's change the signs. And what that leaves me with is 3x minus 4. Now, there is no way to multiply x squared by anything other than a fraction to give me 3x. So, what I can do here then is realize that 3x minus 4 is my remainder. So my solution here, my quotient, would be x plus 1 plus the remainder, 3x minus 4, over the divisor, x squared minus x. And this would be our answer for problem B. Again, with problem B, there is no way to do synthetic division because the divisor is of degree 2. Taking a look at problem number 2, we get from, we're actually moving from division of polynomials into actually multiplication to create polynomials. So in problem number 2, it says write the standard form equation for the polynomial p of x displayed in the graph to the right. So in order to find the equation here, we need to look at a couple things. We see that this function is opening down in both ends. So if both ends of a polynomial go the same direction, we know it's going to have an even degree. Because it's going down, we know that it's going to have a negative leading coefficient. The other way that we can figure out information about this polynomial is taking a look at its zeros. So this polynomial has 3 zeros. It has the zero x equals 2 here. This 0 would be x equals 9. And this 0 over here would be x equals negative 8. What this allows us to do is come up with factors for p of x. So p of x factors have to give us this 0. So p of x has to have a factor of x plus 8, which would give us the 0x minus x equals negative 8. Has to have a factor of x minus 2, and it has to have a factor of x minus 9 to give us those zeros. Again, we said it needs to have a negative leading coefficient, so let's put a negative sign out in front. The other thing that we may notice is that this graph bounces off of 2 at x equals 2 and passes through x equals negative 8 and x equals 9. So we don't know for sure the degree of the polynomial. You can start to figure out what that might be by the number of terms. It has to be at least degree 4 because it has 3 terms in the graph. But we do know that to pass through x equals negative 8 and x equals 9, those factors have to occur an odd number of times. To bounce off x equals 2, that factor has to occur an even number of times. So the x minus 2 has to be squared. So now we can multiply these factors together. And this will give us the standard form for p of x. So I'm going to leave the negative out in front. What I'm actually going to combine through distribution is x plus 8 and x minus 9. It doesn't matter the order that you multiply, but let's take x plus 8 times x minus 9. So x plus x is x squared. I'm still leaving the negative out in front. If I did distribution, I would have a positive 8x and negative 9x. So if I combine those terms, that would give me negative x. And then I would distribute negative 9 to positive 8, and this would give me a negative 72. I'm also going to do the distribution here with x minus 2 quantity squared. So this is squaring a binomial, so that would give me x squared minus 4x plus 4, based on our rules for multiplying binomials. Now I have to distribute these two polynomials to one another. So I'm first going to distribute the x squared. So x squared times x squared, again, leaving the negative out in front of everything. X squared times x squared is x to the 4th. Then I would have x squared times negative 4x, which is negative 4x cubed. And x squared times 4, which is 4x squared. Then I would distribute this negative x, and I'm going to line up my like terms. So negative x times x squared would be negative x cubed. Negative x times negative 4x would be positive 4x squared. Negative x times 4 would be negative 4x. And then one more distribution here. Distribute the negative 72. So negative 72 times x squared is negative 72x squared. Again, I'm going to line up my like terms there. Then a negative 72 times a negative 4x would be positive 288x. And then finally, negative 72 times positive 4 would give us a negative 288 there at the end. And now I want to combine my like terms. So if I combine my like terms, I would have x to the fourth. So p of x is going to start with x to the fourth. But remember, there's this negative sign outside. So I'm going to distribute this negative sign as I go. So this would be negative x to the fourth. This right here would give me a negative 5x cubed, but now I distribute that negative to that, so give me positive 5x cubed. I'm going to run out of room. Let me move this over real quick. Then I would combine the 4x squared, and the negative 72x squared, which would give me a negative 64x squared, but then distribute the negative over there. So I would get positive 64x squared. Then combine these two would give me positive 284x, but again, distribute the negative, so negative 284x, still running out of room slightly, minus 288. So my final answer for p of x would be negative x to the fourth plus 5x cubed plus 64x squared minus 284x minus 288. In problem number three would be an honors only type problem. So school level guys, you will not expect to see imaginary units on your exam. But let's go ahead and go over problem number three. It's still a good review for both. Problem three says we're now looking for a fourth degree polynomial p that has integer coefficients and only one real zero. Given that for p of x, x equals 1 and x equals 2i, write the polynomial in standard form. So again, we're looking to write it in standard form. It's the fourth degree, so we know like the last one, our highest term is going to be a fourth power. It says it only has one real zero, only one, and it gives us these two zeros. So if we're given those two zeros, we know that p of x in this case is going to have a 0, x minus 1, correspond with x equals 0, and a 0, x minus 2i. One thing that we know about imaginary units is they come in pairs. So if I'm going to have a factor that's x minus 2i, I'm also going to have a factor that's x plus 2i. So this right here would give me a polynomial that's degree 3. It has 3 factors. We need it to be a fourth degree polynomial. And we need it to only have one real zero. So here I have one real zero, two imaginaries, it's degree 3. To make this degree 4, I can square one of the terms. Well, I know that I can't square an imaginary term here because then this would give us a polynomial that does not have any solutions. So I'm going to need to square the first term. So now I have a fourth degree polynomial with one real zero, that would be x equals 1, and x equals 2i, and x equals negative 2i. So now, like the last one, we can multiply. So if I just take x minus 1 and I square it, this would give me x squared minus 2x plus 1. If I distribute an x minus 2i to an x plus 2i, this would give me x squared plus 4. And now I would need to distribute again. So x squared times x squared would be x to the fourth. Negative 2x times x squared would be negative 2x cubed. 1 times x squared would be x squared. Then distribute all of those terms to 4. X squared plus 4 would be 4x squared. 4 times negative 2x would be negative 8x. 4 times 1 would be 4. So my final answer here for p of x in this instance would be x to the fourth plus 2x cubed plus 5x squared minus 8x plus 4. So taking the factors and the zeros of a polynomial to establish the standard form of that polynomial. Let's go ahead and take a look at the next question, problem number 4, which is finding zeros through factoring. So in problem 4, it says factor each of the following functions completely, writing repeated factors in exponential form, then list all solutions of the polynomial. So in the previous problem, basically we took the factors and got to standard form. Now we're given standard form and we want to get to the factors. So we're going the other direction. So problem 4a, this one would be kind of an honors only problem. So I'm going to come back to that problem in a little bit. But 4b, we would see at both levels, school level and honors. So let's go ahead and take a look at how we might factor this. This is a quartic function. So we do have the option of factoring this similar to a quadratic function, if the numbers work. So I would like to ideally factor this into two binomials. And the numbers do work here. I can factor this into coefficients with, two binomials with both terms x squared as their first term, because if I take x squared times x squared, that's x to the fourth. I know that one of these would have to be a positive or an addition of two terms and the other a subtraction, because I need two numbers to multiply together to give me negative 36. I also need two numbers that when doing distribution, the result would add together to give me 5x squared. So if you said a positive 9 and a negative 5, in this case, you would be, sorry, not a negative 5, but a negative 4, you would be correct. So we want to factor this down a little bit further. Remember, we can factor a difference of two squares, but we cannot factor together or factor a sum of two squares. So if I want to factor x squared plus 9, I need to change this into a difference. And I can do this by using I squared. So x squared plus 9 is the same as x squared minus 9i squared. Remember, I squared is just negative 1. So it's an equivalent way to write the expression. The reason I can do this is because now I can factor this into a difference of two squares. So this would be x plus 3i and x minus 3i. So if you were to do the distribution of x plus 3i and x minus 3i, that would give you x squared minus 9i squared. The same thing can be done with x squared minus 4. We can break that down as a difference of two squares into x plus 2 and x minus 2. So this would be the fully factored version for p of x. In this case, there are no repeated factors. All of the factors are different, and so there would be no multiple powers of an individual factor. Now in A is a similar problem. The concept or the goal is the same here, but the process is going to be a little bit different. What we may look at in A is we may look at trying to group this. And that's probably where most people would go, is trying to group this. But if I did the process of grouping and pull out a 4x squared, that would give me x plus 2 in parentheses, and then pull out a negative 3, that would give me x plus 3 in parentheses. And so this one doesn't work with grouping. You could try to rearrange the terms, and you're going to find out that it's still not going to work. So we did, honors guys, again, we did talk about finding the list of all possible rational solutions. Remember, the list of all possible rational solutions are factors of the constant divided by factors of the leading coefficient. So this is what we labeled as P over Q. And it would be the set of all positive or negative rational numbers. So factors of 9 would be 1, 3, and 9. All over 1, because that is a factor of 4. Each of these would also be over 2. 1 half, 3 halves, and 9 halves. Because 2 is a factor of 4. Each of these would also be over 4, because 4 is a factor of 4. So 1/4, 3/4, and 9/4. This is the list of total possible rational zeros. So if a rational zero exists for h of x, it's one of these numbers. Now we want to find a rational zero. And we can do that through the process of synthetic division. So remember, if you do synthetic division with a 0, its remainder is going to be 0. So from this list, we can choose one of these numbers and try synthetic division to find out if that is in fact a 0. Now a shortcut here to see if positive 1 works. That's always the number I would check for first. Positive 1 works if you add all the coefficients together, and that gives you 0. So if I add up the coefficients of this list, 4 plus 8 plus a negative 3, so minus 3, plus negative 9 or minus 9, it does give me 0. So I know that 1 is going to be a 0. This is a shortcut for finding out if 1 works. So if I do synthetic division with 1, the remainder should be 0. So let's go ahead and do that. Let's take the coefficients of h of x, 4, 8, negative 3, negative 9. It does not skip any values there, so I don't need any 0 placeholders. Let's go through the process of synthetic division. Bring down the 4, multiply by 1, add down the column. Multiply by 1 again, add down the column. Multiply by 1 again, add down the column, and it does give me a 0. So what I know is h of x can actually be factored here into x minus 1, and this polynomial that would be the result of dividing by x minus 1, which is 4x squared plus 12x plus 9. So now what that does is it breaks this 4-termed polynomial down into a 3-term polynomial that we might be able to factor. And if I break this down, this x minus 1 is going to stay the same. I'm going to factor this into 2x and 2x, because 2x times 2x multiplies to give me 4x squared. Could also possibly try 1x and 4x, but I'm going to go with 2x and 2x right now. I need two numbers that multiply together to give me 9, and that through distribution would add together to give me a 12x. And that would be plus 3 and plus 3. So that would give me 6x, 6x, which adds together to give me 12x. So h of x can be factored into this expression. The factors x minus 1, 2x plus 3, and 2x plus 3. We do see some repeated factors there, so I can list this as x minus 1 times 2x plus 3 quantity squared. And this would be our answer for h of x. So using factoring techniques to factor h of x and p of x in A and B. Let's go ahead and take a look at problem number 5. That skill is actually going to be used partially in problem number 5 as we get down a little bit lower. In problem number 5, we need to graph the following functions using correct x and y intercepts and show our work if we're going to need to do some work. In problem 5a, there's not a lot of work to do. What we need to be able to find is the x and the y-intercepts. So what I know here is my x-intercepts come from my factors. So the factor x minus 7, this would give me an x-intercept of positive 7. So if I took x minus 7 and set it equal to 0, the solution, the 0, would be x equals positive 7. So I'm going to go over here to positive 7, and I'm going to put down a point. And this is going to be one of my zeros, and it's shown on the graph as an x-intercept. Another 0 would become from x plus 1. So if I took x plus 1 and set it equal to 0, that would give me a negative 1. So x equals negative 1 is another 0. Finally, I'm going to have a 0 where x minus 2 equals 0, so at positive 2. So these are the locations where it's either going to touch or cross the x-intercept, the x-axis. To find my y-intercept, basically y-intercepts occur where all the x's are going to be 0. So it occurs on the y-axis, and any location on the y-axis, x is 0. So what that would give me is a negative 0 minus 7, which is negative 7 squared, times 1 times negative 2, putting in zeros for all the x's, or basically eliminating the x's. So if I do that here in my calculator, don't necessarily have to, but that would be not going to multiply by 1 because that's not going to change anything. This would give me a y-intercept of 98. So let's go ahead and just put this y-intercept of 98 down. Notice the y-axis is not scaled, so we don't actually have to count out any lines. So I'm going to put a point on here and make this 98. Now, to get the rest of my graph in here, I know the y-intercept, I know the x-intercept. To get the rest of my graph, I need to look at the leading coefficient. The leading coefficient is negative. This tells us what's going to happen on the right side of the polynomial. The right side of the polynomial is going to be approaching negative infinity on the y-axis, or going down. To figure out what happens on the left, we need to look at the degree. This function has a degree of 4. So squared plus 1 for a total degree of 4, which means it's an even function. Remember, for even functions, even degreed functions, sorry, not even functions, but even functions with an even degree, both ends go the same direction. For functions with an odd degree, both ends go different directions. So that means it needs to go down over here on the left. So my graph needs to go through or touch each one of these points and go down as it goes to the left forever and it goes to the right forever. The other thing to notice that's special on this graph is x minus 7 is a factor that occurred twice. So at x minus 7, this graph is actually going to bounce at that 0 here. It's going to touch, bounce off, and change direction. So what my graph is going to look like is it's going to come up here, it's going to touch, it's going to bounce off this one and go back down. So somewhere in between the 0 of 7 and the 0 of 2, it's going to turn around. It's going to go through 2. Somewhere in between 2 and negative 1 on the x-axis, it's going to turn around and come back down. I'm going to draw it through that y-intercept and draw it through my last x-intercept. And there we have a sketch of the graph for g of x. Now, if you want to, you can type this into your calculator and check that, and you would see that the graph's not going to look exactly the same because the scaling's a little bit different, but it is going to hit the same important x-intercepts and y-intercepts. Now, let's take a look at b. We want to do the same thing with b, but with b, we don't actually know the zeros. This function in b is not factored. So we want to factor it like we have in example A or B. Now in A or B, we use different factoring methods, and in for A or B, we had different factoring methods. In 5B, we're going to use another different factoring method. Again, we may look here and try to group this, but we may notice that this problem here is not going to be factorable by grouping. So if it's not factorable by grouping, it's a third degree polynomial, we're going to have to look for possible rational zeros. So P over Q. School level guys, if you have to factor, and you will have to factor a graph to get a polynomial, you're not going to have to use the P over Q. So you would be able to group, or you'd be able to factor down into two binomials. But again, possible rational zeros here would be factors of 6 over factors of 2. So factors of 6 would be 1, 2, 3, and 6 all over 1, and also 1, 2, and 3, 6 all over 2. So 1/2, 2 over 2 is just 1, 3 over 2, and 6 over 2 is just 3. So these are our possible rational zeros. I may check to see if 1 works by taking the leading coefficients and adding them together. That's not going to result as a 0, so that does not work. I could also check quickly to see if -1 works by taking the opposite of the leading coefficients with an odd degree term, so like changing the -2 to a +2, keeping the 3 here because its term is squared, changing the sign of 11 because its term is to the first power, and then keeping -6 as it is. And this doesn't result in 0, so -12 does not, or so -1 does not work. So we need a number other than 1 or -1 as a 0. Let's try 3. Let's go ahead and try 3 and see if 3 works here. So again, I'm going to take the leading coefficients for g of x and complete synthetic division. If my remainder is 0, 3 is a 0 of this polynomial. So drop the -2, multiply by 3, that gives me -6. Add down that column, and then repeat this process. And I do come up with a remainder of 0. So that means that Again, this is not the only way you could possibly, you did not have to choose 3 first, but if you did choose 3 first, you see that g of x is factored into x minus 3 and negative 2x squared minus 3x plus 2. I'm actually going to factor a negative out of this second set of parentheses because that's probably going to make it a little bit easier to factor. So let's go ahead and rewrite this as a negative x minus 3 and then 2x squared plus 3x minus 2. So I'm going to leave the negative x minus 3 part alone, and I'm going to try to factor this, so splitting it apart into 2x and x, because 2x times x gives me 2x squared. Then I already know that my only factors here for negative 2 would be negative 1 and positive 2, or positive 1 and negative 2. I need to make sure that they're in the right place. So if I do 2x minus 1 and x plus 2, this would give me negative x and positive 4x, which would add together to give me a positive 3x. So this is the factored version of g of x. What this allows me to do is figure out my zeros. My zeros would be x equals 3, x equals 1/2, and x equals negative 2. So if I went ahead and set each one of those factors equal to 0, these are my zeros. So I'm going to go ahead and graph those. So negative 2, 1/2, that's going to be between 0 and 1 there, and then 3. Now, I also know that this has a negative leading coefficient. So I know that it's going to be going down to the right. If I go back to look at the original standard form of the equation, I can find the degree is 3. So this is an odd degree polynomial, meaning the ends are going to go in opposite directions. Finally, the last thing I need is the y-intercept. So I could substitute in 0 here and find the y-intercept, or I could do it up there, which is a lot easier. This would be 0, 0, 0, minus 6. So I'm going to put a point on here and call this negative 6. And these are the points that I need to hit with this correct in behavior to give me my graph. None of these factors occur more than one time, so it's going to pass through each one of them. So this graph is going to go up here from that negative 2, moving to the left. It's going to come down somewhere between negative 2 and 1/2. It's going to turn around. It's going to go through my y-intercept. It's going to go through 1/2, somewhere between 1/2 and 3. It's going to turn around, and then it's going to carry down through 3, and then approach negative infinity on the y-axis. And so this would be the graph for g of x. So in order to graph a polynomial in standard form, we do need to first factor it to find the zeros, and then use the zeros to find x-intercepts, list the y-intercept, and then use the in behavior to draw on the curve. Let's continue forward in graphing, looking at rational functions. This problem, problem number 6, would be an honors only type question for the end of the year assessment. So school level guys, again, it's good review, but it's not going to be required of you. There's a lot of components that we need to take a look at for rational functions. And I'm going to go ahead and start by listing these. So there in the directions, it does tell us to list important key features. The intercepts, the y-intercept and x-intercept, the asymptotes, could potentially be vertical asymptote or horizontal asymptote. Remember, we did not do slant asymptotes. And to list the domain of the function. So in order to get these, the first thing that we want to do is we want to completely factor the function. So if I factor the numerator, it factors into x and x minus 2. And if I factor the denominator, it factors into x minus 1 quantity squared. So to come up with all of these different components, we have different rules. Remember the y-intercept? To come up with the y-intercept, you substitute in 0 for all the x's. We can make it a little bit simpler for a fraction and substitute in 0 for the x's in the numerator. Because if the denominator, you put in zeros for the denominator, it's just going to be a value, a constant. So the 0 of the numerator over that is going to give you your y-intercept. So in this instance, we just have to look at the numerator, because if I put in zeros for the numerator, this would just give me a 0 here in the numerator. So 0 over anything is just 0. So my y-intercept is going to be 0. Let me change colors so we can see the graph a little bit. And then I'm going to go ahead and graph that point. My x-intercept. X-intercepts come from the zeros of the numerator. So not putting in 0 for x, but actually finding what values for x would make the numerator only, equal 0. So if I set this x equal to 0, that would be 1. X equals 0. And if I set x minus 2 equal to 0, that would be the other. X equals 2. So these are the two places where it's going to cross the x-axis. Vertical asymptotes come from zeros as well, but they come from zeros of the denominator. So the denominator is x minus 1, quantity squared, so zeros of the denominator would be x equals 1. So I'm going to put a dotted vertical line there at x equals 1. This is my vertical asymptote. So we are going to approach that asymptote either going up or going down. We do know that x minus 1 is squared. So at this vertical asymptote, we're either going to approach it going both up, or we're going to approach it with both going down. We'll come back to that later. The horizontal asymptote. Remember, the horizontal asymptote had a set of rules. So to find the horizontal asymptote, we'd compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is y equals 0. If the degree of the numerator is equal to the degree of the denominator, which is it is in this case, we take a ratio of the leading coefficients, which is 1 over 1. So in this case, y equals 1. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. And we don't see any examples like that. Now, the other thing that we want to check, we want to make sure, is that this graph does not cross the horizontal asymptote. Or if it does cross the horizontal asymptote, we want to make sure that we have that location there. So it's going to approach the horizontal asymptote towards infinity on the x-axis and towards negative infinity on the x-axis, but we need to see from which side to see if it crosses. So to do that, you take the equation and set it equal to the horizontal asymptote. So x squared minus 2x over x squared minus 2x plus 1 equals 1. So if I multiply both sides by the denominator, that would say x squared minus 2x equals x squared minus 2x plus 1. And then if I subtract x squared and add 2x, this would say 0 equals 1, which is false. So this does not cross. And now we have enough information to draw in our sketch. So what we know is that we have to cross the x and y-intercept here. We have to cross the x-axis here. We do need to know that it approaches this vertical asymptote going the same direction. So it can't go up, because then it would cross the horizontal asymptote, which we cannot do. So it's got to, from these points, it's going to go down. Getting closer and closer to that asymptote, but not crossing it the further it goes down. To the left and to the right, it's going to approach the horizontal asymptote. So it's going to go through our x-intercepts, and it's going to get closer and closer and closer to this horizontal asymptote as you go further to the left and further to the right without crossing. And there's our graph for this rational function. So this is the graph for 6a, and you can check that looking at a calculator. 6b is very similar. So let's go ahead and do 6b. So I'm going to go ahead and factor the numerator. So the numerator would factor into 2x squared minus 4, and then that would factor into 2 times x minus 2 times x plus 2. The denominator would factor into x minus 4 times x plus 1. So my y-intercepts would be found by setting all the x's equal to 0. So basically what that would leave me with is negative 8 over negative 4. So negative 8 over negative 4 is just y equals 2. My y-intercept is here at 2. Then my x-intercepts are zeros of the numerator. So if I took these two factors, set them equal to 0, I would get x equals positive 2, and I would get x equals negative 2. So I'm going to have 2 points on the x-axis. My vertical asymptotes would be zeros of the denominator, which would be x equals 4 and x equals negative 1. So I'm going to go ahead and sketch those in as vertical lines, and I'm going to use dashed lines to again represent that we are approaching this value but not actually crossing this value. And then finally, my horizontal asymptote, if I look at my rules, the degree of the numerator is the same as the denominator. So I take a ratio of the leading coefficients. So y equals 2 over 1, y equals 2 is the horizontal asymptote. So notice here that we already see a location where this function crosses the horizontal asymptote. So we know that this is going to cross at x equals 0 on the y-axis. Let's make sure that's the only place. So if I take 2x squared minus 8 over x squared minus 3x minus 4, I set that equal to 2, the horizontal asymptote. I'm going to multiply by the denominator on both sides, so that's going to give me 2x squared minus 8 equals 2x squared minus 6x minus 8. And then I could subtract 2x squared, they would cancel out. I could add 8, they would cancel out. 0 equals negative 6x divided by negative 6, so x equals 0 is the only place that it does cross. So now I can draw in my curve here. So what I know is I only have intercepts, x-intercepts at negative 2 and positive 2. So if I start over here on the right and I want to figure out where my curve is going to be, I know it can't be down here at the bottom, because if it was down here in the bottom, it would look something like that, approaching the correct asymptotes. You can't do that because then it would cross the x-axis. So this graph, we don't even need to necessarily plot any points. We're just going to sketch a representation of it. This graph is going to have a curve in the upper right, over here to the right of this graph. In the middle section, I know that it's got to go through each of these 2 points. It's going to have to pass through each of those 2 points. What I also know is that none of my horizontal or vertical asymptotes were repeat factors. So if I'm going up to the right of this vertical asymptote, I need to go down on the left side of this vertical asymptote. So this graph has to be coming down over here. It's got to go through the point 2 because that was a factor that only occurred once. It's not going to bounce. So it crosses through here. It does cross the horizontal asymptote at x equals 0, that point that we found right here. And then it's going to approach the vertical asymptote there. Finally, our last curve starts at, it's going to go through the x value of x equals negative 2. It's going to approach the vertical asymptote going down in the opposite direction that this one went. And it's going to approach the horizontal asymptote going to the left. It cannot cross the horizontal asymptote because the only place we could cross was at x equals 0. And this would be a graph of our rational function. Again, you can check this in the calculator. I forgot on the last problem to talk about domain, so let's go ahead and do that now. Remember, the domain is all real numbers except for the zeros of the denominator. In this case, the vertical asymptotes. So the domain would be all real numbers except for 4 and negative 1. On the previous problem, the domain would still have the same concept. It would be all real numbers except for the zeros of the denominator, which would just be 1. And there we have examples of graphing rational functions. Problems get a little bit shorter, a little bit faster after those. So let's go ahead and let's take a look at problem number 7. We are moving forward a unit here and actually getting into inverse functions and one-to-one relationships. So in problem number 7, it says to identify which of the following graphs represents a one-to-one relationship and explain how you came to that conclusion. So remember, functions that are one-to-one have relationships between inputs and output of the function. So For a graph, to identify if something is a function, we use the vertical line test, and that determines if each input is related to exactly one output. For a function to be one-to-one, each output also has to relate to a single input. So we would use not only the vertical line test, but the horizontal line test. So if I take this vertical line and I pass it through number 1, we can see that 1 is a function, 2 is a function, 3 is not a function, 4 is a function. Now if I take this vertical line and I switch it to a horizontal line, 4 we said was a function, but it fails the horizontal line test. So it has some output values that correspond to, or some, yes, output values that correspond to the same input. Same thing for problem number 2. It has some some output values that correspond to the same input. And if we look at number 1, it does pass the vertical line test. So graph number 1 would be the only possible option that we have here for being a one-to-one function. Now you could explain this a number of different ways. So an example of an explanation might be that you'd say graph 1 and say because it passes the vertical line test and the horizontal line test. Or another option could say to be graph 1 because each each input has only one output, and each output has only one input. So a one-to-one relationship means that each x value is mapped to one y value and one y value only, and each y value is mapped to one x value and one x value only. Problem number 8 gets into inverse functions. So remember, inverse relationships basically take the x and the y coordinates and switch them. So in problem number 8, it says the graph of the function y equals g of x is shown to the right. Use the graph to answer the following questions. So it says evaluate the inverse of g of -1. So remember, this notation right here means inverse. So the inverse of g of 3. This would be the same as looking for g of x equals 3. So basically what we're looking for is a location on this graph where the y value is 3. And we have 2 locations. Both of these 2 points would match up. And so we could say that this answer would be either 1 or maybe -3.25, somewhere in between -3 and -4. So if we're looking for an input value for the inverse, that corresponds to an output value of the original function. Vice versa, it says for b, solve for the variable in g of the inverse of x equals -3. So in this case, if we take that kind of inverse relationship, we'd be looking for the g of -3 equals y. So where I find that point on the graph is right here. G of -3 equals y. Sorry, I put 0 in there, but 0 would actually be the correct answer. So in this case, x equals 0, because the x value of -3 corresponds with the y value of 0. So if I take the inverse of that for the relationship, it would be 0 corresponding with -3. Problem number 9 would be one, again, that deals with inverse functions, but this would be one that we would see on probably an honors-only exam. It says algebraically find the inverse for each of the following functions. So what we want to be able to do here is take f of x and get its inverse. Now we can do that graphically. We can look at pictures and we can take a look at coordinates, but the quickest way to do that for a function algebraically, that's the key here, algebraically, is to take the x and y values and flip them. So remember, f of x is the same as y. So basically what I can do is change this into x equals y cubed plus 1. Now I want to solve for y. So I would subtract 1 from both sides. And then to get rid of cubed, I would take the cube root. So y equals the cubed root of x minus 1 would be the inverse. Or if we wrote this in inverse notation, the inverse of f of x, so f to the negative first power of x equals cubed root of x minus 1. We can do the same thing with b, h of x. This one's a little bit more complicated, but same concept. So I'm going to take h of x, which is y, and now make that x. And I'm going to take x and change that into y's. Now notice here that there are two y's. So we do have to do a little bit more work to get y by itself. So what I can do here is multiply both sides by y plus 1. So if I multiply both sides by y plus 1, that leaves me with x times y plus 1 equal to y. Now I can distribute x, y times x plus x equals y. Now if I'm trying to get y by itself, I want both the y's on the same side, so I'm going to subtract y and subtract x. And now this still doesn't allow me to completely get one y, but what I can do is factor here. So factor out a y, and so that would leave me y times x minus 1 equal to negative x. Then I can divide by the quantity x minus 1. So this would be y equals negative x over x minus 1. So the inverse of h of x is negative x over x minus 1. So in order to find an inverse function algebraically, we want to take the x and the y portions of that function and switch them, then solve for y. Now let's go ahead and take a look at another example, problem number 10. This would be a problem that we would see at both. It says to determine algebraically if g of x is the inverse of f of x. So we talked about a way that we could do this algebraically through function composition. So if I take f of the inverse of f of x, basically I take f of x and substitute it into the inverse of f of x and substitute it into f of x, that's going to give me just x. So I can do that here. See if these are inverses of one another. I can substitute one function in for the other. So let's take f of x, which is the 2/3 x minus 6, and substitute in g of x. So I'm going to do f of g of x. So I'm going to replace the x value in f with g's entire expression. And then I would simplify this. So 2/3 times 3/2. So 2/3 times 3/2 is just 1. So this would be x. 2/3 times negative 9. 2/3 times negative 9 would be negative 6 minus 6. So if I simplify here, I would get x minus 12. So f of g of x is x minus 12. These are not inverses of one another. To be inverses, they would have to simplify through this composition to give me just x by itself. So these are not going to be considered inverses. You can do the same process for b. So take either function. It doesn't matter which way you do the function composition. So in this case, I will take f of x and put it in for g of x. If you did it differently, that's okay. We should come out with the same answer at the very end of this, though. So if I take f of x and I put it in for g of x, this would now be the cubed root of x minus 4 cubed plus 4. So replacing this x with f of x. So the cube and the cube root cancel each other out, so I'd get x minus 4 plus 4, and then I would get x. So g of f of x is x, and so these are inverses. So function composition can tell us if two functions are an inverse or not, if once we result, or the result of the function composition should be the original input value. Taking a look at problem number 11, problem number 11 is in the same unit, but it starts to change topics into exponential and logarithmic functions. And so this problem says to use the uniqueness property to solve for the variable. So we want to solve this using what's called the uniqueness property. Basically, the uniqueness property means that if I can get these two to be of the same base, then their exponents have to be equal. So we want 8 to see if I can make 8 the power of a number that I can also make 32 the power of. What I can do here is I can rewrite 8 into 2 to the third power. So 8 is basically rewritten as 2 to the third power. Why this is helpful is I can also rewrite 32 as 2 to a power. This would be 2 to the fifth power. So I can simplify this expression. Remember, two exponents, taking the power of a power, we would multiply. So this over here on the left would be the same as 2 to the 3x plus 6 power. To the right, I'd have 2x to the fifth power. So now, because I have two bases that are the same, the exponents have to be the same. So 3x plus 6 equals 5. Subtract 1 from both sides, and then divide by 3. So x would equal negative 1/3 in this instance. And you can always check that by taking negative 1/3 and substituting it back in, and you'd find that this would work. Let's go ahead and do the same thing for b, the same concept. So let's break these two down into a number that they can both be the same power of. In this case, we could use, again, the number 2. So 32 can be rewritten as 2 to the fifth. 16 can be rewritten as 2 to the fourth. Then if I simplify both sides of the equation, this is 2 to the 5x power equals 2 to the 4x plus 1 power. So because the bases are the same, the exponents must be equal. And then I can subtract 4x, so x equals 1. Sorry, I made a mistake. When I distribute here, this should be 4 times x plus 4. So in this case, x should not equal 1, x should equal 4. The concept is still the same. Make the bases the power, or make the bases the same, but with different powers, and the powers have to be the same. In problem number 12, we are taking a look at graphing exponential functions. So I'm going to show you how to do this without the graphing calculator, but you will have the graphing calculator to help you in this process. Let's start with B, actually. B is going to be a little bit easier than, sorry, the second B. This should be listed as A, but let's start with B. This one's going to be a little bit easier. First thing that we want to do is take a look at transformations. Remember that exponential functions look something like this. Before transformations, all exponential functions have the point 0, 1. We want to see how that transformation, or how that function has been transformed, or how that point has been transformed. So what this right here would do, this negative 10 on the outside, this would be a shift down 10. So I would go from negative 1 down 10 units. This x minus 2, because this x minus 2 is inside the operation, this would be a shift right 2. So I would move it over right 2 units. And so this would be my initial point for the exponential function. Remember, exponential functions also have a horizontal asymptote starting at x equals 0 before transformations. So the shift down 10 would move that horizontal asymptote down here at x equals negative 10. Now, the base 4 tells us how to get all of the rest of the parts of the exponential function. This is an exponential growth because the base is greater than 1, and also because there's no reflection here. So if I move to the right 1 unit from my initial point, I'm going to be 4 to the first power units above the vertical asymptote. So 4 to the first power would be 4 units above, or sorry, the horizontal asymptote. If I move from the initial point right 2 lines, I'm going to be 4 to the second power, which is 16 units above the horizontal asymptote. If I moved over another line, 3 lines from the right of that initial point, that would be 4 to the third power, which would be 64 units way off the page. And I'd keep going, 4 to the fourth power, 4 to the fifth power, until you have enough points that would carry you off the page. If I went back the other way, it would be 4 to the negative 1 power, so it would be negative 1, 4, and so on and so forth. But this would also, we also know that it's going to approach the asymptote because it's an exponential growth. It's going to approach the asymptote going towards the left. So then we can sketch in our curve here. And if you graph it, you should have something that looks like that. Again, we approach the horizontal asymptote, we do not cross it. The domain for this function, the domain is going to be all real numbers. So this function is going to stretch to the left forever and to the right forever. The range for this function, it does go up forever, but it's not going to go down forever. The closest that it's going to get, keep getting closer and closer and closer and closer to negative 10, but it's never going to cross or touch negative 10. So y is going to be greater than negative 10. The same concept applies here for a. So first, it's exponential, so I'd have a point here at 0, 1, but I'm going to get a vertical shift down 1. I have no horizontal shifts, so my initial point is going to be at 0, 0. I have a horizontal asymptote that got shifted down 1, so that horizontal asymptote is going to be at x equals negative 1. This is an exponential growth. Remember, e is approximately 2.7, so e is going to be a number greater than 1, so it's going to be another exponential growth. I have no no reflections. I do have a dilation here, a vertical stretch. So the dilation is going to affect all points other than our initial point. Our initial point does not change. So if I move to the right 1, if I move to the right 1 power, or 1 spot, this would tell me to go e, the base e, to the first power units above the vertical asymptote. But it's being stretched by 2, so I'm going to double that distance. So I'm actually going to move up 5.4, approximately 5.4 units from the vertical asymptote. So, sorry, horizontal asymptote. 1, 2, 3, 4, 5, and a little between 5 and 6. Here's my point. If I moved over another line, this would tell me to move e to the second power units above the asymptote, but again, that's going to be doubled. So I would move up 14.8. This would carry me well off the page, but if I were to do this, I would count up 14.8 points, and I'd be up somewhere around here. If I went the other way, it would be e to the negative 1 power, e to the negative 2 power, but we also know that it's going to approach this horizontal asymptote going to the left, as it is exponential growth. And so our graph would look something like this. The domain here, again, would be x equals all real numbers. It's going to stretch to the right and to the left forever. The range is going to be greater than, in this case, negative 1. So you will have your graphing calculators with you as well to help you get these functions. But if we are asked about the transformations, please remember how your effects and transformations change graphs. Let's take a look at problem number 13. Problem number 13 is basically getting us into the relationship between logarithms and exponential functions. So remember, logarithms and exponential functions are inverses of one another. And so we can use logarithms to rewrite exponential functions. And we can use exponential functions to rewrite logarithms. In the expression here in problem 13, we want to rewrite these into exponential form. So the base of the logarithm can be found here. In an exponential function, the way that we write that base is just the 2. The power of the exponential function would be found here. So this would be 2 to the third, and then that would equal 8. And we know that that makes sense. 2 to the third power is 8. Do the same thing for b. So our base in this case is the subscript number 3. Our power is the output value, 2. in the logarithmic expression, and the input value in the logarithmic expression becomes our output value for the exponential expression, so 3 squared equals 9. Same concept on the last one. Our base is 7. Our output from the logarithm, because the input for the exponential, and our input from the logarithm becomes our output for the exponential. In 14, we're going the other direction, but it still follows kind of the same concept. Now, our base is the number we see written here. So then we would write this as log base 4. The output of this function, 64, becomes the input of the logarithm. So log base 4 of 64 equals, then the input of the exponential becomes the output of the logarithm, 3. In B, our base is E. So when our base is E, we would have log base E, but remember log base E can be rewritten as the natural log. Our input value for the natural logarithm would have been the output value for the function. So the natural log of 20.086 is equal to 3. Finally, the last one here, we're going to change this into a log. We have a base of 1/3. The output for the exponential, 27, is the input for the logarithm. And the input for the exponential, -3, is the output for the logarithm. So this is basically just talking about the relationship, the inverse relationship between logarithms and exponential functions. Moving on. Problem number 15. Problem 15 says, state each of the transformations shown in the following functions and then graph the functions, listing both domain and range. So now we are graphing logarithms. I'm just going to talk through the transformations. I'm not going to write them out. Logarithms are similar to exponentials, but they are inverses. So a logarithm would look something like this without transformations. So instead of having a point that's at 1, 0 like in exponentials, it has a point that's at 0, 1. This point is going to be shifted up 3, so we have a translation up 3. This is the only transformation we have in 15a. So we're going to shift this point 0, 1 up 3, and now it's at 0, 4. Now, this is our initial point. Remember, for exponential functions, we had a horizontal asymptote, and this horizontal asymptote was affected by shifts up or down. For logarithms, we're going to have a vertical asymptote. This vertical asymptote is going to be affected by shifts left to right. There are no shifts left to right. So the vertical asymptote is x equals 0. Ooh, I think I made a mistake on my exponentials. I labeled these as x values. I did. This should have been y equals -1. I labeled this as x equals 10. That should have been y equals 10. Sorry. Small point, but I wanted to make sure I corrected that. So my vertical asymptote, back to this problem, 15a, my vertical asymptote is x equals 0. My curve is going to be a growth because it is of base 2, which is greater than 1. So it's going to grow and stretch out to the right. Now, with exponentials, we moved right 1, and then we moved up powers of the base. For logarithms, we're going to change that around. We're going to move up 1 from the initial point and move over powers from the base. So my base is 2. If I move up 1 from the initial point, I'm going to be 2 to the first power units from the asymptote. If I go back to my initial point and I move up another line, so I move up 2 lines, I'm 2 to the second power units from the asymptote. Then if I move up another line, I'm 2 to the third power units from the asymptote. If I moved up another line, I'd be 2 to the fourth power units, which is 16 units from the asymptote. If I went back the other direction, so I moved down from the initial point, I'd be 2 to the negative first power, and then 2 to the negative second power. But we also know here we're just approaching the asymptote. So the positive 3 is our only transformation there. It was a vertical shift up 3. The rest of the information deals with getting the correct location to put points for our curve. So the domain for this function, the domain for exponentials, as we have seen, has been all real numbers. The range for logarithms that we will see will be all real numbers. So this goes down forever and up forever. moving left to right, it does go right forever, but as we move towards the left, it gets closer and closer to this line, but never crosses. So x is going to be greater than 0. Let's take a look at B. B follows the same concept. Vertical shift, I do have one here. This is vertical shift is down 2. I also have a horizontal shift. Remember, this is inside the operation, so this horizontal shift means right 1. So I'm going to take this point that's initially at 0, 1. I'm going to move right 1 and down 2. So this is my new location for my initial point for my graph. This is a logarithm base E. Base E. Oh, sorry. Before I get to the base, let's go ahead and move the vertical asymptote, because the vertical asymptote is going to be affected by the horizontal shift. So it's going to move over to the right one. So I'm going to have a vertical asymptote at x equals positive 1. The base for this logarithm is E. So here's my initial point. I'm going to move up 1. And this is going to tell me that at this location, I'm going to be e to the first power units from the asymptote. I do not have any stretches. I do not have any vertical shifts, or sorry, vertical stretches or vertical compressions. So I'm about 2.72 units from the vertical asymptote. So a little bit between 2 and 3. Again, this is 2.7 units from the asymptote. So 1, 2, almost to 3. If I move up another line, I'm e to the second power units from the asymptote. So this would be about 7.38. So if I count from the asymptote, I'm moving up one more line. If I count from the asymptote, over about 7.4, would be right about there. The next one would be e, the next line up would be e to the third power units from the asymptote, which is about close to a little over 20, so that would stretch well off the page here. If I wanted to move down from my initial point, this would be e to the negative first power, e to the negative second power, and so on and so forth. You can sketch those in if you like, but we could also just go ahead and draw it in approaching the asymptote. So this one had 2 transformations, a vertical shift and a horizontal shift. The domain for this function is going to be x is greater than 1, everything to the right of this vertical asymptote. The range for this function is all real numbers. So graphing logarithms and graphing exponentials is very similar, but again, they are inverses of one another. Problem 16 says to algebraically determine the domain for the following functions and show your work. So if we want to have a domain value, remember with logarithms, let's go back to the previous function. The domain was greater than the the vertical asymptote. So basically what we have to find out is where's the vertical asymptote. So essentially what we know with logarithms is we cannot have a negative input value. So if I take this function for a, x plus 1 over x minus 3, this value has to be greater than 0. Okay, so if I want the function to be a value that is greater than 0, for this function, either the numerator and the denominator have to be less than 0, they both have to be negative, or the numerator and the denominator have to be greater than 0, they both have to be positive. So I have to consider this being a fraction. So in order for the entire fraction here to be greater than 0, I have to have that the numerator and the denominator are the same size. So x plus 1 and x minus 3 is greater than 0 would be one possible outcome. So in this case, x minus 1, x plus 1 is greater than 0, x would have to be greater than greater than negative 1. And x would have to be greater than 3. So if x is greater than negative 1 and also greater than 3 here, x is greater than 3 would be part of my domain. The other part of my domain would be that if x plus 1 was less than 0, and x minus 3 would also be less than 0. So in this case, x would have to be less than negative 1, and x would have to be less than 3. When x is less than -1 and less than -3, x is less than -1. So the domain for this one would be x is greater than 3 or x is less than -1. Fractions are by far the most complicated versions of these. Let's take a look at B. Again, the input value has to be positive. So 9 minus x squared in this case has to be greater than 0. So if I want to solve this here, I would subtract 9, or maybe let's go ahead and add x squared. So 9 is greater than x squared. Now I can take the square root of both. Sorry, let's actually, let me do this a little bit differently. Let's factor this. So if I factor this, this would be 3 minus x and 3 plus x is greater than 0. Get that right. 3 minus x and 3 plus x is greater than 0. So I can break these apart. 3 minus x is greater than 0, and 3 plus x is greater than 0. So then if I solve for this, 3 is greater than x, and 3 is greater than negative x, or x is greater than -3. So basically what we could say if we wanted to write this in one expression, x is between -3 and 3 for this function. Finally, for C, the input value is this square root expression. So the square root of 5 minus 3x has to be greater than 0. In this case, what we know is that if it's a square root, in order for it to be a real number, the expression inside of that square root by itself has to be greater than 0. So 5 minus 3x has to be greater than 0. So I could add 3x, so 5 is greater than 3x, divide by 3, so x is less than 5 over 3. So if we want to find the domain for a logarithm without graphing, or algebraically find it, we set the input value greater to 0, and then solve for x. Let's go ahead and section this up. So this is going to be the end of part 1 for the end of the year assessment study guide. For more answers, go ahead and tune into part 2, which will be posted to YouTube as well. Thank you guys for tuning in. If you have questions, go ahead and shoot me an email.